Hello, we are from Group 13 and today we will be presenting the project we have chosen for this assignment, which is the pulse code modulation system for secure data transmission in financial transaction. There are 5 members in our team. Pulse code modulation, PCM, offers a solution for secure data transmission, leveraging digital signal processing to enhance both reliability and security. PCM is a method used to digitally represent analog signals, converts analog input into a sequence of coded pulse, thereby enabling efficient and secure data handling. This report analyzed the use of PCM in financial transactions, emphasizing how it can enhance data transfer integrity and lessen common security risks. PCM also provides a multi-layered defense against fraud and data breaches by transforming analog signal into a digital format. There are a few objectives in this project, and this project main objective is to investigate the use of a PCM system for financial transaction security.
For the operational mechanism, each modulation technique has its unique operational mechanism. For pulse code modulation, PMC is a technique that used for reworking analog signal into digital signal. It consists of sampling, quantizing, and transmitting digital values. PMC begins with sampling the analog signal at a regular interval. Each sample is then quantized into digital value, meaning it is assigned a discrete value from, from a finite set of labels. Then it will introduce quantization noise. After that, the quantized value are converted into a binary code with a fixed number of bits per sample. For pulse width modulation, PWM is a technique used to convert a digital signal into an analog signal. PWM generates pulse with varying width. During modulation, the width of the pulse is varied in accordance with the amplitude of the analog input signal. To indicate various signal level, the duty cycle or the percentage of a cycle changes when the pulse is high. The width of each pulse is proportional to the amplitude of the signal, while the frequency remains constant. Lastly, for data modulation (DM), the technique is used for analog to digital and digital to analog signal conversion. Transmitting value is different between consecutive samples. During encoding, this technique employs the use of the single-bit PMC coding to achieve digital transmission of analog signal. By approximate the analog signal with a staircase waveform which move up or down by a fixed amount delta at each sampling interval. Instead of transmitting the absolute value, DM transmits the difference between successive samples for simplification.
Hello, I'm going to explain about advantages and disadvantages of each technique, and the first one is pulse code modulation, PCM. PCM has noise immunity compared to analog digit signals. PCM signals are less prone to noise and interference. The signal can be broadcast over great distance with little degradation once it has been digitalized. Next, PCM effectively and simply enable the transmission of several channels over a single communication link, or time division multiplexing (TDM). However, the disadvantages of PCM is its complexity. PCM systems require more intricate circuitry for encoding and decoding procedure, which can raise the cost and the power consumption. Next is its bandwidth requirements. The transmission of PCM require a larger bandwidth. The sampling rate and the amount of bits used for quantization determine how much the bandwidth is required. Next is the advantages of pulse width modulation, or PWM. PWM has high efficiency at delivering powers, particularly in applications like motor control and power regulation. This is because PWM can reduce power loss in switching device and appropriate for battery-operated gadgets. Other than that, PWM offers exact control over the output voltage and current. An example of needing precise control is lowering the brightness of LED lights or regulating motor speed. PWM also comes with the disadvantages. The first one is electromagnetic interference or EMI. The switching that occurs quickly in PWM can potentially produce electromagnetic interference, which could harm the adjacent electrical device. PWM also has complex filtering. Low-pass filtering is necessary to convert back PWM signals to analog form. This process can be complicated and may not accurately recreate the original signal, especially in lower switching frequency. The last technique of modulation is delta modulation or DM. The advantages of DM comes in its simplicity compared to other modulation such as PCM. The DM encoder and decoder are less complex. The circuitry complexity of DM and expense are decreased by its simplicity. DM also has low bit rate, where it can achieve a reduced bit rate by encoding only the changes between samples. This is beneficial for application with constrained bandwidth. Last but not least, the disadvantages of DM is granular noise. Granular noise happens when the failure of DM to precisely match the minute variation in the signal. Granular noise may result from a step size that is too large for signal that fluctuate slowly. DM also have lower signal to noise ratio or SNR. Generally speaking, DM has lower SNR than PCM, particularly for complex signal with fast fluctuation. The quality of reconstructed signal may suffer as a result. That's all from me.
This presentation provides a breakdown of a code that simulates secure data transmission in financial transactions using pulse code modulation (PCM). Step 1. Transaction data to be transmitted is acquired. Step 2. Transaction data is encrypted to ensure security during transmission. Encrypted data is converted into an analog signal, then centered around 0. Step 3. Analog signal is quantized into discrete levels based on the specified number of bits. Step 4. Quantized signal is encoded into binary format for transmission. Step 5. Noise is added to the binary signal to simulate a noisy channel during transmission. Then binary signal is decoded back into quantized value upon reception. Step 8. Analog signal is reconstructed from decoded quantized values. Step 9. Decrypted data is obtained from the reconstructed analog signal. Step 10. Ensure the integrity of transmitted data after encryption, transmission, and decryption. Step 11. Measure the quality of transmission by calculating the bit error rate (BER). Step 12. Measure the time taken for the entire process, crucial for real-time financial transaction. Finally, the original and reconstructed analog signal uploaded for visual comparison, providing insight into the effectiveness of the transmission and reconstruction processes. For the result, data integrity value of 0 signifies a failure in ensuring the integrity of the transmitted data. By addressing potential causes of data integrity issues and implementing improvements such as error correction, encryption enhancement, and format consistency checks, the system can achieve higher reliability and integrity in secure data transmission. PCM introduced minimal latency, mainly due to the processing time for sampling, quantization, encoding, and encryption. This latency is generally acceptable for secure financial transactions. A BER or bit error rate of 0 indicates that the noisy bit stream exactly matches the original bit stream. This means no bit error were introduced during the transmission and noisy addition process. In ideal condition, a BER of 0 suggests an ideal or nearly ideal condition where the noise added did not cause any bits to flip. This can be due to a high signal-to-noise ratio, SNR, ensuring that the noise impact is minimal. The code also ends by producing plots that contrast the original and reconstructed analog signals. The graphs produced by the code illustrate the comparison between the original and reconstructed analog signals. In the result, the original analog signal graph depicts the analog signal before any manipulation or transmission, representing the raw data such as financial transaction details. On the other hand, the reconstructed analog signal graph portrays the analog signal reconstructed after undergoing the entire transmission process, including quantization, encoding, noise addition, decoding, and reconstruction. This reconstructed signal reflects the data after it has been processed for transmission and then restored back to its original analog form. This visual representation offers valuable insight into how well the transmission and reconstruction processes maintain the integrity of the data. The system effectively handles data integrity, latency, and bandwidth efficiency, much like a pulse code modulation PCM system designed for the secure data transmission in financial transactions. A key goal is ensuring that the reconstructed signal closely resembles the original one, indicating the PCM process success in maintaining signal integrity. Any noticeable differences may result from quantization noise arising when approximating the continuous analog signal with discrete level during quantization. However, in an efficient PCM system, such differences should be minimal. The system tracks the processing time encompassing encryption, quantization, encoding, transmission, decoding, and decryption. This facilitates the monitoring and improvement of latency to guarantee efficient and prompt processing of financial transactions. Although the code simplifies latency measurement, real-world scenarios emphasize the critical importance of latency, particularly in financial transactions demanding timely processing. PCM systems are naturally efficient in terms of bandwidth usage as they depict analog signal by utilizing a limited set of discrete labels. This diminishes the volume of data necessary for transmission while retaining the crucial details inherent in the initial analog signal. The bandwidth demand is directly linked to both the sampling rate and the quantity of quantization levels. In scenarios requiring heightened security, elevated sampling rate and increased bits per sample may be employed, consequently escalating the bandwidth necessity. Nevertheless, this approach guarantees enhanced precision and security.
Next, we'll be talking about the performance of the system. There are three main areas of remarkable performance in the simulation result of the developed pulse code modulation system for secure data transmission in financial transactions, which are signal-to-noise ratio, system responsiveness, and error rates. First of all, the system attains a high signal-to-noise ratio of 30 decibel. A high SNR implies that the signal is much stronger than the noise, which is necessary to preserve data's clarity and lower the chance of data corruption during transmission. SNR is a metric that compares the strength of the signal to background noise. With an SNR of 30 decibel, it is possible for the system to send data clearly and discernibly even in situations when there is a lot of noise interference. The second one is error rates. The system achieves excellent error rates with ideal result of 0 for both the bit error rate, which is BER, and data integrity check. This means no mistake occurred during the transmission, showcasing the system ability to uphold data integrity. This high level of accuracy is especially crucial in financial transactions, minimize error, and ensure secure communication, thereby preventing losses. The last one is system responsiveness. The system responds quickly with a latency of about 0.016072 seconds. Latency measures the time it takes for data to travel. For financial transactions, fast response times are essential to avoid delays and keep clients happy. These systems' quick processing ensure transaction happens smoothly and on time.
Next, we'll be talking about the improvements and justifications for the system. Firstly, to improve the system, we need to have enhanced noise handling, which is to use sophisticated error correction coding methods like turbo codes or LDPC codes. It is important for secure financial data transmission when data integrity is critical. We need to integrate adaptive filtering techniques such as Wiener or Kalman filters, which adapt in real time to changing noise characteristics. Secondly, we need to have increased bandwidth efficiency, and we need to optimize bandwidth utilization using techniques like differential encoding, such as delta modulation or DPCM. We need to also apply compression algorithms, such as arithmetic coding and wavelet modifications, which are effective ways to reduce data size without sacrificing data integrity. Next, to improve the system, it needs to have robustness to channel variability. First, diversity reception. Techniques for space diversity and frequency diversity help to provide dependable data transmission by reducing the impacts of channel fading and fluctuation. Second, adaptive equalization. In order to minimize distortion, strategies like adaptive equalization dynamically modify filter parameters dependent on channel conditions. The last step to improve the system is having dynamic adaptation. Adaptive modulation and coding, AMC, dynamically modify modulation and coding schemes based on real-time channel quality. Second, cognitive radio approaches, using real-time interference and usage information to dynamically allocate available spectrum bands. Intelligent spectrum allocation systems maximize spectrum utilization. In conclusion, a solid and dependable method for secure data transmission in financial transactions is to implement a pulse code modulation system. Because PCM is digital, there is less chance of signal deterioration and illegal access during transmission, which improves data security. This is especially crucial for the financial industry, as mistakes and data breaches can reveal critical information and result in large financial losses. In a nutshell, by offering precise and secure data transmission, a PCM system improves the security and dependability of financial operations. Future developments in PCM technology and security protocols will strengthen its position in the safe transfer of financial data. That is all for our group. Thank you.